So you guys are all studying electric vehicles? Okay. So we've been talking about the problem of transportation here. And we are saying that the problem of transportation is an unsolved problem across the world. There is no solution which is running in the market today, in cities today. And it's as hard a problem as finding a cure to cancer. Alright, I'll just give you a quick summary of what we have been talking about. And these problems are related to congestion, high cost, carbon emission, pollution, and so on. So what we're going to do, you came just in time, like you came just in time for a very interesting exercise, where we're going to solve that problem. We're going to solve in this room, like you are in first year. In this room, we're going to solve a problem which nobody across the world has ever solved. That's an amazing idea. So this is the starting slide for that. And for solving this problem, let's set a goal. Let's say that okay, let's solve for speed, and then when we have a solution to that, then we can come back and look at other goals like efficiency and other things. So let's focus on speed. How do we get a high-speed transport solution? How do we provide a high-speed transport solution in a city? Now, let's say this is the layout of a city. These spots you see here, these are, let's say, origins and destinations, like where you want to go from and to these places. So these are scattered, like these are scattered in the city. And you want to find a solution. Let's say we set a goal of say 100 kilometers per hour. Like we want people to travel from any of these places to any of these places at a speed of average speed of 100 kilometers per hour. So I want to be clear. Like I'm not talking like we talk about maximum speed of 100 kilometers per hour. Like your car can already do that. How do we enable people from any of these points in the city to any of those to travel at an average speed of 100 kilometers per hour? So you want to go from, let's say, X to Y, and we want people to go from 100 kilometers per hour. Similarly, you want people to go from any point to another. So step one, what we do is that instead of the shortest path is straight line. So I think if people are somehow crisscrossing each other in a straight line, that will be a mess. That's not going to work. So we can't let people crisscross each other. Just take the shortest path. So we have to optimize that a little bit, and we do that by stringing together all those points in a network, in a grid. All right. So now, once you have a grid, then all traffic is on a line on a grid. Then all traffic is going in one direction. Okay, so you don't have crisscrossing traffic. So you don't have people hitting each other trying to get to their destination. So we are running. Everybody is running in one direction. Everybody is driving in one direction. So at least that risk is gone. Now, let's say, just imagine any of those 2 points. Like, let's say, look at so let's go back to this one. And imagine, let's look at this point. You want to go from here to here, or you may want to go from this point to this point. How would you go? You could go from this point to this point. Like, imagine it's running clockwise. The traffic is running. So let's pick up just two. You see my mouse? Okay. So let's just pick up two sets of journeys here. So this is, let's say somebody wants to go from here to this place, and there's another guy who wants to go from this origin to this destination across. And now we have strung together all of these points into a smooth grid. And now, let's say the traffic is on all of these lines is running clockwise. So it's going from top to bottom here, and from bottom to top here, and from left to right. So you have a path. So you want to go from, this guy wants to go from here to here. So you can see that there is a path, right? This guy wants to go from here to here, this thing. So there is a path to that. So that you can take this path. Now there's another problem. So the problem is that there are other stations along the way. There are other locations along the way. So you gotta keep stopping. So how do you go? So if you want to achieve high speed, you need to be able to go to your from your origin to your destination non-stop. Alright, so I think absolute speed of 100 km per hour is not a problem, it's a solved problem. There are many vehicles that can run at a speed of over 100 kilometers per hour, so that's not really what we're worried about. What we are worrying about is how do we avoid stoppages? If we could go from any point to any other point at the speed of 100 kilometers per hour, then it's not the problem of speed. So what we do is that we add bypasses to each of these locations. So if you want to go from, let's say, here to here, we provide bypasses. Like, you don't have to stop here. So you can then go non-stop from any of these points to any other points, to any of the other points. So that's how we solve for the problem of speed. You think this can work, right? Does it make sense? Is there, you think this simple solution, like, right? It's feasible, right? It's practical. So that's what, my startup is doing. So we are solving this problem.
In this direction.
Yes.
If you go in opposite direction to the adjacent point.
Yes. Right. So see, if you go, I am not going into the details of it right now. So different types of networks. So what you are seeing is one type of unidirectional network. So so this is two-dimensional unidirectional network, meaning it's spread out in 2 dimensions. But there could be a 3-dimensional unidirectional network where you can have lines crossing over each other, like a flyover. You could also have a bidirectional network where you have, instead of one line going, you have actually close to each other that are going in opposite directions. So I'm just keeping for the purpose of our understanding and keeping it simple, but yes, you can have different types of network. You can have elevated lines, you can have underground lines, you can have all kind of things, options. So that's what we are working on. So I want to take you through the details, some of the high-level details of how we are coming up with a solution. So this is an example. This illustration is an example of an elevated line, but this line can be also at grade or it can be underground as well. This is another unidirectional network. So these are stations, and you can maybe it will be larger, but I think you can see that these are offline stations. So if you want to stop, if somebody wants to stop here, they will have to first go offline, they take the secondary line, and then come to a stop. So that those who don't want to stop here, they can keep going straight. So now in this network topology, you can go from any point, any origin to any destination non-stop. And if you see here, you can see there are 2 lines going in opposite direction, very close to each other. So you can imagine that if we bring these 2 lines a little closer, they become like a bi-directional line. This is an illustration of how it would look visually. Now in this picture, we are running at grade. So I think yesterday somebody mentioned trams. Right, in our so it's a tram-like network on the ground. In terms of cost, it's low, but it's subjected to interference from other trams. But this is possible. Something like this is possible. This is another illustration of what we are doing. In this case, the pathways are dedicated, so they are non-stop. They are what we are working on. These lines will be extremely slim, very thin, and you will see them today. You will get a flavor. I'm not saying you will see exactly this today. You will see a lab and you will see things in lab environment. which are a bit crude, they don't look so nice and polished. But you will see that these are actually very thin lines, they don't occupy much space. Sorry?
Speeds to be same for all the
Yes, so on a particular line, they all travel in one direction, the same direction, and they must travel at exactly the same speed. So it's like car lane, like in a
They will
lane.
be of speed like 120 km per hour.
Yeah,
Everybody should go with 120 km.
right. And these are, remember, these are autonomously driven, like no humans are driving this. And that's important because otherwise it will be hard to keep the speed same. So these are driven under, so these vehicles are coordinating among each other, they're talking to each other, and they're running at exactly same speed so they don't run into each other. So how now how practical is this? On the right there is an actual picture of a tram system. We use lesser space than tram. Our vehicles are much smaller and we don't have this overhead captain. So these are some more pictures. So it's in India. I'm not saying that we should use tram-like system, like grade system, but it is practical. In India, I think the elevated systems and underground systems will work better. So now, as I said, these systems these vehicles are autonomously driven, and many people compare us with autonomous vehicles. So they say that Google is developing autonomous cars, Uber is developing autonomous cars. Like Tesla has already got level 5 autonomous driving, level 4 autonomous driving. So how are we different? Like why are you using tracks? Because that adds to the cost. Like to lay down the cost with the tracks, and that adds to the infrastructure. Like in case of, let's say, Tesla or something, like automatically you don't have to lay down the tracks. It's running on the road. But then you're stuck in the traffic. Like, it doesn't really matter. If you have an automated car, like the only thing is that you are not driving it, you're just sitting idle. But the car is still subject to same environment. It's still stuck in traffic, the costs are still high, in fact higher, and the cost of autonomous driving in cars is very high. It's unaffordable. And all of those problems that we talked about in the beginning, those problems are still there. But when we put them on dedicated tracks, and these tracks can be made grade separated, you achieve many more advantages. So let's say if we talk of high energy efficiency, I think, so you talked about railways and energy efficiency in railways. So railways today is the most energy efficient mode of transport. And the reason why railways is so energy efficient is because you have steel wheels that are on steel rails. And steel rails offer extremely low coefficient of friction. So you get very high energy efficiency. And as of today, there is no other mode of transport that is anywhere close to the efficiency of railways. Now, how do we beat that level of energy efficiency? The problem with railways, especially in the context of urban transport, like you have metro rail, for example, you have 2-3 problems there. One problem is that, let's say, during peak hours and non-peak hours. So during peak hours, railway, when the trains are full, you get very high energy efficiency per unit, like per person move. But during non-peak hours, when the trains are running empty or half empty, for example, in Bhopal we have metro rail, it's running practically empty. Its energy efficiency is disastrous. Like, technically you have very high energy. You have stop travel. So you start, you pick up speed, maybe you set speed of 70-80 kilometers per hour, then within 1 minute, 2 minutes, you have to slow down, apply brakes and come to a stop. And then again start. Now you have regenerative braking in railways, you can recover some of that energy, but regenerative braking also, you can recover maybe I think 50-60% energy, something like that. Right? So you still
Practically 30%.
yeah, practically 30%. So, so railways being being so efficient, because of these practical issues, they are still, and at the end of the day, it's still not that efficient. So, but in case of our solution that we together invented just now, all your travel is non-stop, and you are moving only when there is a passenger demand. So, if during our non-peak hours, let's say in the afternoon or late night, early morning, when there are no passengers, say only those many vehicles move for which you have passengers. The rest of the vehicles are simply waiting and standing at the station waiting for passengers, and when they move, they go non-stop. So you don't have a start and stop type of travel. So we take the benefit of railways technology because we are also running on steel rails. So we get that energy efficiency, but we are slightly better because we don't have those two problems. Now, if you look at capacity, we can achieve enormous amount of capacity when we run on rails. Now, our